Good evening, sir, and welcome you all to the second day of the session. And I'm handing over to the speaker. Sir, you may continue.
Yeah, sure. Good evening, all. So yesterday we have covered uh, basics that is required for writing a Verilog code of a combination circuit like half-adder, mux. These all we covered, and different modeling also we have covered. So today we will be doing the same in EDA background, and I want to give you guys an idea how to do that in EDA background. So I written the design code of half-adder in data flow model. You can see here. It's visible, right?
Yes, sir.
So the same code I have written, nothing changes there. If you guys have any doubts in this design part, you can ask. We have covered that yesterday. So I'm going to cover today this test bench part. I want to give you an idea how to write the test bench and how we verify the design. Okay. So we will be starting same like module test bench. So for test bench, usually we don't have any ports. We will be basically test bench is written for verification purpose during the simulation part. Okay. So we will be writing our test bench with the keyword module. Then test bench name, I'm giving just TB, or you can give any other name. So here we won't have any ports. That's why I'm directly writing semicolon instead of writing bracket and writing ABC, those things. That won't be requiring in test bench. And we will be requiring either register or wire to keep the variables. So when I'm talked about this reg type, I said like register is having the capability of storing values. It's like a memory. So here, whatever inputs we have designed in the design part. So we have inputs like A and B, right? So those will be acting as a register in this test bench. So this A and B is not same as this A and B. That's why I've written it as capital and small letter to understand these two are different. How we map this to this, I will explain. So first we need to understand is whatever input we are putting in the design, that will be a register over test bench. Okay. Then outputs will be wire, same as in the design part. Then the mapping part. Before going to that mapping section, I need to discuss gate level modeling one more time. In the gate level modeling, we have said like we will be using primitive gates like and we will be giving an instance name of A1 and we will be putting some output and some inputs, right? This is in our design, we are using these variables. And in the primitive and there will be like some out what so variables like out in one in two. So these primitive inputs and outputs should be mapped to our design variables. So we are mapping like out to O, A to I1, B to I2. Like that we need to map. So this is one kind of mapping according to the position. That's why when I told like whenever we are writing our primitive gates, first you have to follow output then inputs, right? If you are writing A, O, B, A will be treated as output. So that's the positional mapping. The other mapping is on based on what name. So you can like out of O dot I1 of A dot I2 of B. Just I'm giving an example, okay? So maybe this variables won't be the primitive variables. So I want to give you an example of how to do the mapping. Okay. So if I'm saying like I want to design a, let's say I need to design a full ladder using half adder. So for full ladder, we will be having three inputs, A, B, C, and we will be having two outputs, sum and carry. And in half adder, we will be having two inputs and two outputs. Right. So whenever we are designing this, we will be getting like A, and this S is given to this and C, and we will get S here, and this is C2, and this C1 and C2 are over, and we will get carry. So I will write it as carry. Okay, so this is our half adder, and entire design is a full adder using half adder. Okay, so this digital part you won't care about now. I want to explain how we are going to design a full ladder using half adder in gate level modeling. That's only. Okay, so we will be writing like module full ladder. We have three inputs, sum and CO. Then input A, B, and C. Output S and C0. So we need two half adders. In this interconnects, we have S1, C1, and C2. So we are going to write it as wire. We need S1, C1, C2. Right? Then we need an half adder. So what we usually do is we will be saving this half adder module in the same location, like in the same directory. Otherwise, you can define the half adder code above of this module. The same half adder code what we are writing here. The same half adder this code, design part of this code you can write here, and you can call that half adder here. It's like a calling the function of one module inside another module. Okay. We need two half adders. I am giving this instance as H1 name, and this is H2. So H1, and let's say I have taken inputs as A comma B comma S comma C for our half adder. Okay. So our first A should be mapped to capital A, B should be mapped to capital B, our sum should be mapped to S1, and carry should be mapped to C1. This is the first instance. Then the second one, H2, A will be mapped to S1, B will be mapped to C, S will be mapped to S, and C will be mapped to C2. After that, I am using one assign statement, or you can use OR gate if you want. Assign CO equal to C1 or C2. And 1. Understood? Then like A, B, S, and C, you can write H1, A, B, S1, C1, HA2, S1, C, S, C2. This also you can write if you know the position of the uh, what the module you are going to instantiate inside the design. Okay, here it is half adder. Clear? Any doubts in this? Okay, so moving on. So in the test bench, similarly, I have written this half adder inside the test bench. Okay, so I wanted to map this half adder inside the test bench that we are going to test. So I have written HA, instance name H1. Then I'm mapping the signals. So we have in the half adder, we have S, C, A, B as our uh, ports. So that port is mapped to our test bench signals like dot A of A. This A is mapped to this A. This B is mapped to this B. C is mapped to C. S is mapped to S. And yesterday I talked about always block. Like when I discussed the behavioral model, I used an always at asterisk this kind of statement once. So we have two kind of procedure block we have. We have always and we have initial. The difference between these two is initial block will be executed at time of the simulation t equal to 0. Always block will be executed whenever the sensitivity list or whatever conditions we have applying to this always block, then only it will get executed. And always block can be put in a loop, but initial block will get only executed once. Okay. So here I am using an initial block, initial. Because of multiple statements inside that, I am using begin and end. So inside that, I am giving first in at t equal to 0, I am giving a equal to 0, b equal to 0. Hash 10 means after 10 nanoseconds of delay. Nanoseconds, I got the unit from this time scale. If it is 1 nanosecond by 1 nanosecond, which means that the time unit will be in 1 nanosecond. If it is in picoseconds, then this also will be in picoseconds. If I'm giving 1 second, then it will be in 1 second. Okay. Then divided by 1 nanosecond is our precision. So many After dot, how many zeros or ones you can mention. That's the precision time. Okay, if I am using S10, here it means for 10 nanoseconds. So after t equal to 0, we are giving a equal to 0, b equal to 0, and it will wait till 10 nanoseconds, and it will give a equal to 0, b equal to 1, and it will wait another 10 nanoseconds and give 1, 10. Then 10 nanoseconds delay, it will give a equal to 1, b equal to 1. Understood this initial block? This the same I am using the truth table here. I am giving 0, 0, 0, 1, 1, 0, and 1, 1. All conditions I have given. Then usually when we do this in Vivado, we usually don't use this initial block, this part of the code. But in EDA playground, when we want to use the EP wave, we need to have a dem file, that is dem.bcd file we need to open that in EP wave. It will record all the variables and their values in the particular type, and that will be plotted in EP wave. So this is common, and you can change this delay means according to your design. Like if I am having more than 50 here, I need to provide more than 50 here also. This is only 30. I've given 50. You can give also 40. No issue. And this finish is one system task. There are another system task also. We will discuss that later. Finish is used to put the stop to the simulation. After 50 nanoseconds from t equal to 0, the simulation will get terminated. Okay. So when we run this code, so we need to select the tool and simulator I'll tick, as I discussed yesterday. And we need to tick this open EP wave after run. Then we need to write all these things and click run. And the log will get printed here. If any error is there, it will get printed. If it is not there, then it will open the EP wave. As you can see here, we're having A, B, C, S, and capital A, B, C, S. Because of this dot C BCD file, it will plot all the variables that are present in the design. So we can delete. If you want to delete, click on that and click this X button. It will get deleted. If you want to delete, otherwise leave it there. I only want these 4 variables to explain the truth table. Just taking this particular time period at 10 nanoseconds. At that time, we are giving 0, 1, right? After 10 nanoseconds, I am giving the value A is 0, B is 1. At that time, sum will be 1, right? So S is 1 here and carry is 0. You are able to see this, right? And at 20 nanoseconds, after 10, again, I am waiting for 10 nanoseconds, right? So after 20 nanoseconds, I am giving A equal to 1, B equal to 0. At the time also, sum equal to 0, sorry, sum equal to 1, carry is 0. And in 30 nanoseconds, I'm giving A is 1, B is 1. At that time, carry will be 1 and sum will be 0. That's the thing. Understood? So this is EP wave. And if you are making any mistakes or any syntax error is there, it will be logged in this. Uh, Suppose I'm making like this. Okay, I want to show you the error. See, in test bench, line 19, in this block, there is something missing. That's they are saying like syntax error. So you need to find out what are the errors when we are writing the code. This most common thing, like we will forget to put semicolon, those things. It happens. Okay. So that's the first thing I want to discuss today. So we have covered how to design a full adder using half adder in gate level modeling, how to instantiate the module inside a module. Then we have covered the EDA playground with the one half adder design, and test bench, how to write the test bench, what is delay, how the delay unit is defined. Then what is the use of VCD file. These all things I have covered. Now I want to go for a little further to behavioral modeling. Any doubts in between, you can ask. Okay. So in behavioral modeling, first I want to discuss one combinational circuit of mm, give me a sec. Okay. So behavioral modeling. Okay. So decoder I am going to design. Decoder 2 to 4 decoder. Okay. So we will be having 2 inputs and 4 outputs. So I'm naming it as A and B as our input and Q0, Q1, Q2 as our output. 0, 0, 0, 1, 1, 0, 1, 1. And our decoder will be 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. This is our truth table. And we need to design this part in Verilog using behavioral model. Okay. So the code will be module decoder A comma B comma Q0 Q1 Q2 input A comma B output Q0 Q1 Q2. So yesterday when I discussed marks, I said like in behavioral modeling our output should be reg type. So I said output should be reg type because whenever we are using some variable inside the procedural block, like in initial or always block, it should be a reg type. So let's say in the design part, we don't require the output should as a register and it should be a wire. Then internally we can define one register. Like here I am defining like that and I will explain with the same code that we have written yesterday. We are using some other variables like Q0, Q1, Q2. These are our 3 registers and always at A comma B, or you can use asterisk sign. Okay. Begin case. Yesterday I used if else, so I want to show you how to use the case statement. Case bracket A comma B. What this curly bracket means is concatenation. Concatenation is something you can combine the two into one. Like if I'm using here A comma B, it will become 2-bit. So we can directly write 2 tick B00. Then for Q0 will be 1, Q1 will be 0, Q2 will be 0. Like this. This is not exact syntax. First, I want to explain how to write the case and how to use the concatenation. So instead of writing like this, you can write separate A and B, and you can write one tick B0, A equal to B equal to one tick B0. Like that also you can write. To reduce the what code line or code length, we can use this concatenation operator. Any doubt in this?
Sir,
Yeah.
the 2 to 4 decoder has 4 outputs, right?
Sure. I wrote only 3, right? Okay.
Yes.
Yeah. Thank you for finding out. Okay, I will start over. K3 also we will be having. Okay, let's say 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Okay, this is the two table. Now we need to design this part in this code. So the change will be we'll be having Q3 also. Q3. And inside the case, we'll be writing 2 tick B00. So if you have multiple statements, we need to use begin. Okay, begin and writing Q small letter. Q0 is equal to 0. Q1 is equal to 0. Q2 equal to 0. Q3 equal to 1. And likewise, you can write 2 tick 0, 1, 2 tick 1, 0, 2 tick B1, 1. These all you can write. Okay. Nothing else there. You can directly write on the touchpads to table. Then for case statement, usually we will write one default statement also at the end. So if someone forgot to write one case of, let's say we have 50 or 60 variables inside this concatenation, and we are forgetting to write one variable inside, and we are writing that condition in the test bench, and we are testing. At that time, this module doesn't know the functionality of that particular condition. So at that time, it will be going to this default path, and we will be printing that particular condition. Here we can give all zeros if you want, or any other conditions to that is priority, then you can give it there. I'm giving all zeros here. Begin and is also there. Okay. So after this, our Q0, Q1, Q2 have the values what are required. Then at the end of this always block, again we will be using assign statement, and we will be giving Q, capital Q0 as small Q0, Q1, Q1, like all will be assigned statements. Okay. So why we are doing this is our Q, capital Q0, whatever that mentioned in the port, it's not a register type. Inside the module, we are declaring 4 registers like small Q0, Q1, Q2, Q3. That should be given to our output ports. That is what I have given here after the procedural block. Inside procedural block, we can't use output ports. That is a wire type. Okay. So this is kind of a messy thing. You can use instead vector, then it will be more looking good code. I will write the same code in different module, decoder, and we have input, and we have out. And I'm saying input is 2-bit, so 1 down to 0 in, and we have an output of 4-bit, so 3 down to 0 of out. So here either you can define another register of 3 down to 0 of X to store the value in the procedure block, and I'm starting always block, always height asterisk begin case of in to take B 0 out, not out, X. X equal to 4 tick B 0 to tick B 1 will be 4 tick B 0 B10 will be 4 tick B 1 will be 1 0 default X is equal to 4 tick B all zeros, and okay, one thing I forgot here, after default, before ending the always block, we need to end the case. To end the case, we use end case. No space is there. Then to end the always block, end. Then we are giving assign out equal to X end mode. So any doubt in this code? You understood how to use the case statement, what is default. If you are not writing the default, sometimes the design will be going into race around condition due to unknown what output. So it will print some junk value, or it will go to continuous ones and zeros. To avoid that, we use in the case statement default condition. So that is decoder code. You understood how to write the combinational circuits code in Verilog. If I'm giving one combinational circuit, you should be able to write the code in Verilog or any model. It should be in either data flow, gate level, or behavior. So the combinational part came to an end. We will be starting the sequential circuit design. Before going into that, any doubts in this combinational design part? Any model or uh, any section of this EDA background design? Anything anywhere? Okay, so the next part is sequential circuit. So we will be designing all the flip-flops that we have. D flip-flop, then we have T flip-flop, JK we have, then sorry. This or we are going to design in Verilog. To how to design this, I will start with D flip-flop. Module DFS. For sequential circuits, there will be a clock in our design. Whenever there is a positive edge or negative edge of the design, then only that particular design is going to work. So for ports, we will be having clock, CLK I'm writing. Then we have an input D and output Q. So likewise in combinational circuits, what I have mentioned that output should not be a register type. In sequential circuit, output will be a register type. So input will be clock and D output the right Q. Okay. So this is our declaration of module name, and ports and their functionality. Then I'm starting the always block. Always at we have clock like this, right? So our flip-flops will be working in the edge of either positive edge or negative edge of the clock. So we have two keywords, pos, edge, and negate. So if you want to work with the positive edge of the clock, we usually use pos edge. And if it is negative edge of the clock, we need you to negate. So I am using here positive edge of the clock. So I am using pos edge of clock. If multiple statements is there, then only you need to use begin and end. Otherwise, you don't need to, but I'm using. It will be a standard practice if you are using that. Then Q less than or equal to D. And end module. I will explain what is that less than or equal to. So till now, whenever we are assigning some variable to other value, we used like this. Q equal to A, S equal to A, X or B. Like this we have till now used. But whenever we are dealing with sequential circuits, we will be using less than or equal to. So the difference between less than or equal to is this is non-blocking assignments and this is blocking assignments. So the difference between this is blocking assignment is executed sequentially. Whatever the order we are giving inside this begin and end, that particular order it will get executed. But non-blocking assignments, it will get executed once, but the updation will take place in the NBA region, non-blocking assignment region. There are different regions in Verilog. There is active region, inactive region, NBA region. So this non-blocking assignments is basically done for sequential circuits, and blocking assignments is usually used for combinational circuits. Okay, so whenever we are dealing something like let's say we need to swap uh, let's see A as 6 and B as 9. I'm taking an example to explain. Okay, so I need to swap A with 9 and B with 6. So what we usually do is we take a temporary variable and we store the particular value of 1, any of these, to that temp variable, and we will give the second variable with the first, and first so we are storing this temporary variable with A. So temp have 6 now, that we are giving to B. So A will be given B and B will be having temp. This is usually we do when we want to swap the values of the two variables. But when we are using non-blocking assignments, you can directly write like this. If A is 6 and B is 9, you can directly like A is B, B is A. Which means that this will execute at the same time at let's say t equal to 10 seconds or 10 nanoseconds. This particular always path or this particular statements assigned at the same time, and the evaluation will take place after that particular time instance. It will seems like a complex thing, but it is not. Only thing you need to remember is whenever we are dealing with sequential circuits, we will be using these non-blocking assignments. We will get to know more about this when you explore this sequential circuit in depth. It won't be that easy to explain when we are dealing with these simple flip-flops. So when we are dealing with FSMs or sequence detectors, then uh, then processor design, those part, then this non-blocking assignments will comes into picture. Okay. Any doubt till here? So this is our D flip-flop code. Any doubt in this code or any doubt in this non-blocking blocking assignments? Everyone understood this postage and nuggets? You know flip-flop is edge triggered, right? If you have any doubts, you can put in chat also. I will read that and give you reply. Okay, moving on to T flip-flop. T is toggle, right? So how to write that code is its symbol module T flip-flop. So I want to give you another way of mentioning these ports and inputs. You can directly mention inside this bracket direct like this input clock comma input T comma output right Q bracket semicolon. Like this also you can mention whatever we are written. Otherwise, you can mention all the ports first and define their functionality like input and output. Usually, I go with this part because when we having multiple uh, what more than 50-60 signals, then we will be forgetting that to mention in the port list, and we will be directly declaring that as input or output. So in this case, we will be mentioning only one time. We don't need to define that again. Okay. So try to design with this. Then always at for such clock begin if t is high. So if I'm mentioning only t inside an if, it is similar to equal to equal to 1. Okay. So equality it's checking like whether it is high or not. If it is high, we are giving q negation of q, else I'm giving q as same and what. So this is so if you want to comment one line, you can use double slash. Then you can mention the comment. So this is toggle and this is hold. So this is toggle flip flop. Whenever t is high, our output will be toggling of the input. Toggling like whatever we are given the previous, that will be toggling and when the input is 0, then it will get hold. Okay. If you don't know these flip flops, when you are studying this in digital design, at that time, you guys design this same in the EDA playground or keyboard or Xilinx, whichever software or tools we have available. We can use that and design. At the point of time, you need to understand how to write the flip flop in a Verilog code and the syntaxes and functionality, how to mention the positive edge of a clock, and how to write that in behavioral modeling. What is the difference between initial and always clocks? These all things you need to understand from this workshop. That's the only thing you need to go through. For basically, I am talking about this to first year students. I think first year are dealing with only gates. I think flip flops are covered in digital electronics. Anyway, whenever you are dealing with that, at that time you guys design. So it will be a like theoretical application you are doing in your curriculum, and practically you are designing parallelly. So it will strengthen your understanding level, how the T flip flop is working. Everything you will get to know when you are doing the simulation. So these two things I am going to design in the EDA playground. Okay. So first we will design D flip flop, then we will go to design T flip flop. So what we have to give is you need to give inside this Q less than or equal to D. And module. Okay. This dump file that I said like that will not be changing. So you can use that initial begin block common for every test points and you are using EDA playground. So here we have clock and D and output wire initial begin and giving D as 0 and after 10 I'm giving D as 1 and after 20 I'm giving D as again 0 and after 5 I'm giving D as 1 and so the way you need to give the clock that is different when you are dealing in test bench. You need to write always at let's say 5 clock equal to negation of clock. So what this means is when you are writing always hash 5 clock equal to negation of clock means time scale is 1 nanosecond. Okay. So every 5 nanoseconds it will toggle the clock. So let's say I'm starting high. After 5 nanoseconds it go to low, and after 5 nanoseconds it go to high, and it will continue forever. That's why we are using always clock there. So this clock will generate like this. Okay. So that's this line represents. And here I am writing like at t equal to 0, I am giving d equal to 0. And after 10 nanoseconds, I am giving d equal to 1. And after that, waiting for 20 nanoseconds. After that, I am giving d equal to 0. And after that, I am waiting for 5 nanoseconds. And then I am giving d equal to 1. Okay. Now, I forgot one thing. I need to map the module here, right? So before initial begin, we need to call this d flip flop and we need to map clock D Q. I'm using positional mapping here instead of name. Let's run this entire. I think there is no error. Let's see. Where is there? Okay. Instance name we have not given instead of I just given like that. Okay. So here clock is not getting any value since we have not given initial value to the clock. So that I have not mentioned. So whenever we are defining a variable, it will have the values 0, 1, x, z. So if you are not defining a variable, the default value will be x, that is don't care. I think you have heard this in KMAP, don't care condition. And this is high impedance. So these all four values can be stored in a variable. So it either can be 0 or 1 or x or z. So if we are not defining the value initially, it will get z. That's why here, not z, x. So that's why here clock is showing only x value. We have not given any initial value to clock. So if I am defining in the initial time clock is 0. Now if we run this clock code, it's so slow. Okay, so now you can see the clock is getting toggled in every 5 nanoseconds. First I have given 0, that's why it's starting at t equal to 0, it is 0. And after 5 nanoseconds, it is toggled to 1. And after 10 nanoseconds, again 0, 1, like that it is going. Okay. Then for 10 nanoseconds, I am first giving d equal to what? 0. Why this q is equal to x here? Can anyone explain? It should be 0, right? Q we are giving here, or here we are giving q equal to d. Then why it is not getting that? Here it is showing some don't care condition. Why?
Sir,
Yeah.
yeah, is it because the transitions occurs at the positive edges only?
Yeah. So we are mentioning in the always block the sensitivity list as positive edge of the clock, right? So whenever we are detecting a positive edge of clock, then only that always block will get executed. So at the 5 nanoseconds, we are detecting a positive edge. At that time only, it will check what the value of D. It is 0, and at the time, Q will become 0. Here you can see. And the next positive edge is coming here. At that time, D value is 1. So Q value become 1. Then the next positive edge, D value is 1, Q value is 1. And the next positive edge, D value is 1, Q value is 1. In between, D is changing to 0. Right? But Q value is not changing from 1 to 0 because there is no positive edge in between. So let's take some different delay. Like instead of 10, I'm taking 8. And let it be 4. And let it be 12. And run this again. So here let's see. So whenever we are detecting a positive edge of the clock, at that time you check. So D equal to 0, so Q will be also 0, right? Here D is changing to 1 here. You can see, right? D is changing here. But at that time, there is no positive edge of clock. So always block will not get executed. And the next positive edge, D is 0, then Q will become 0. And in the next positive edge, D is become 1. And at that time, Q will become 1. And the next positive edge, D is 1, Q is 1. Understood? So that's how it is depending on the positive edge part of the clock. If you are using negative edge, then you should check the negative edge of the clocks. So that's how we check the functionality using test bench and simulation. We will be giving some different conditions here. In the test bench, we can give like random values to D. Still, like we have only two conditions, like either it can be 0 or 1. If it is a multi-bit signal, like 8-bit or 7-bit, there will be more conditions. This is simple code, that's why I have written only 3-4 conditions. For understanding purpose, I have written for 5 conditions. So you understood why this don't care condition is there, and whenever the D is changing, still Q is not changing because there is no positive edge. Then whenever positive edge is there, then the always block will get executed. Whatever we return in the always block, that will get the correct value. Okay. So that's flip-flop, D flip-flop. Any doubt in this? You understood how to write the test bench for this? How to write the clock? How you written that mapping? All things are clear, right? Okay, likewise, you can do the D flip-flop. Now I'm going to cover the SR and JK so that flip-flops we can complete. Okay, so for JK module, JK flip-flop, we have input clock, then input J, then input K, then output right Q. Otherwise, at 4 sets of clock begin is concatenation of J, K. It is 2-bit 00. It will be in hold condition. So the same output will be given. Then if it is 01, it will be reset condition. So Q will be 0. Then if it is 10, Q will be 1. that is set condition, and if it is 1 1, then Q will be negation of Q, that is toggle condition. So this is hold, this is reset, this is set, and this is toggle. Then we can write default. If we are not writing, then it is also not an issue here. So we have covered all the condition. If any of the condition is not there, then you need to write the default. Q, we can give it as 0. Okay, then end case, end model. So this is JK flip flop. For SR, let's say instead of J and K, it will be S and R. And here we will be writing SR. And the conditions will be for 0 0, it will be hold, same. 0 1, it will be say reset, same. For 1 0, it will be set, same. But 1 1, instead of toggle, it will be like for SR, okay? It will be 1 tick BX, which means that it will be invalid. So we are giving don't care conditions there. Okay, and default same, and case and then end module. That's the difference between JK and SR. Only this line will be different, and this variables you can change. Instead of JK, you can use SR. Okay, so all these flip flops, I have not used reset condition. So this reset condition also you can include in the input signal, and it can be either synchronous to clock or asynchronous to clock. Synchronous and asynchronous reset we will be discussing more when we are moving towards that FIFO and FSM. That in next class we will deal with that. So you guys, I will explain one thing here with D flip flop. So same code, let me show first. So this was D flip flop, right? So if I am including a reset condition also. So module D flip flop clock reset D Q. We have input clock reset and D, and output right type Q. Okay. Then in always block, always at both sides clock begin if reset Q will be 0, else Q will be D, and end module. Can anyone say this is synchronous or asynchronous reset? You understood the difference means from this flip flop code to this, I have included one reset conditions also. Included reset. So if I include that here, guys tell me whether it is synchronous or asynchronous reset. If RST. It's Tuesday. And RST, initially I'm giving reset as high. Then after 20, I'm giving reset as 0. At that time, that whenever reset is given 0, at that time I'm giving d equal to 0. Okay, let's try this. Okay, so in the first clock edge, we are given reset as high, so Q will become 0. So D is not defined at that time, that's why it is showing don't care. Whenever we are giving the reset 0, at that time we are giving D value 0, since it is in the whenever means we are given already Q is 0 at that time, so it will continue it whenever there is a positive edge. At that time D is 1, at that time it will change. Here only it is getting changed. We can try different delays and check this out. So with this timing diagram, now you guys say whether it is synchronous reset or asynchronous reset. Yes, guys.
Synchronous.
Any other comments? Okay, so even here reset value is high, our Q is not changing. If reset is high, Q should be 0, right? But here, whenever reset is becoming high, Q is not turning into 0 because it is depending upon the clock. Since in the sensitivity list, we have only mentioned percentage of clock, under this clock sensitive, this reset is working. So it is depending on reset is depending on this clock. So it is synchronous to this clock. So we can say that this reset is synchronous reset. If you want to mention the asynchronous reset, you need to mention percentage of clock, comma, negative reset, or you can use positive edge, no issue. But usually If you write negates, you need to use negation of reset. Yeah. Otherwise, if you are using positive edge, you can use direct. Now what happens? Now let's see. So without depending on the clock, whenever reset is becoming high, our Q is turning into 0. Right? So this is asynchronous reset. So difference between asynchronous and synchronous, you can directly tell from the sensitivity list. Whenever there is mentioning clock and reset in the sensitivity list, we can say that this is asynchronous reset. Whenever only clock is mentioned and inside where reset condition is there, you can say that is synchronous reset. Understood? So for today we have discussed how to design all the flip-flops in behavioral modeling. Then we designed a decoder in behavioral modeling. Then I explained how to use this case and how to use the concatenation operator, how to write the test bench, and how to design a full ladder using half adder, using gate level, how to instantiate uh, one sub module inside a module. Those all things are have covered. Then difference between always an initial block, difference between blocking and non-blocking assignments. When you are planning to go for VLSI job interview, these all things are common questions. What is the difference between these blocking and non-blocking assignments? Why we are going for non-blocking assignments for sequential circuits? Then what is the difference between always block and initial block? These all you need to understand. While designing a Verilog of a digital circuit, you need to go through all these basic ideas. Then only you will understand what we are designing at that time. Even if you are joining in a company, you won't be writing the entire code. So there will be a big code, and inside that some feature enhancement will be there. So you need to add some inside some edits you need to change. One what clubbing you have to do, then some instantiation you have to do, some submodules. These things you have to do it to a big code. So if you don't know how to do all these things, then Verilog is waste. So try to understand in sudden if you are checking a code, you need to able to understand what the functionality actually what is going on there. If I'm giving only this part of the code, like this module, if this will be like 1,000 line, if we have more than 600 or 650 signals, then we will be seeing this always block so many times, always initial, these things you will be seeing. At that time, you will be checking a particular clock at that time what happens, and in the simulation you will check that whether that particular register is getting updated with that particular value or not. Our clock is working properly or not. These are all things you need to verify. So even without the definition of the module, you need to understand what is going on inside that particular module. You will get to understand this while practicing this Verilog frequently. You can even practice this. There is one site, HDL bits. You can try. Verilog practice questions are there. You can write the design. Only you need to write the design code. Test bench is already written there. Then you run the test case, and they will show one waveform with your output and expected output. If it is matching, then it will show like success. So whenever you are getting time, go through that HDL bits. There are tricky questions also, so you will get to know how to solve those. In between, if you have any doubts in solving those questions, you can ask me. Or the answers are available in internet. You can directly search there also. So any doubt in this? Tomorrow we will be directly going to design FIFO, then FSO. We will be using one sequence detector and we will be designing that. And I need to discuss one more part that is known as system task. I only mentioned this finish. This part only I mentioned. So there are other system tasks also that I will explain tomorrow. This dumb file is also a system task. This is also a system task. What all these do, I will explain. Then clock defining, I already explained. So that was coming under the test bench part in the module 6. So module 6 I already covered. In that only that system task is pending. Then in registers and memory, we will be designing shift registers, FIFO, and FSO, sequence detector using FSO. Okay, that we will cover tomorrow. That is little advanced, but I want to cover that. So we will be getting a full exposure of this Verilog. Even if you don't know the design part, don't worry. Okay. Okay, thank you everyone.
Thank you so much, sir. Everyone, please join tomorrow. Tomorrow will be our last session. And thank you for joining. Thank you, sir.